Next problem. So let's solve the same system of linear equation, but this time we will be using Gauss elimination. So again, in matrix form, the system of linear equations will be the same. It has a coefficient matrix, a square matrix, followed by a vector of unknowns, and on the right side will be the vector of constants. For Gauss elimination, we have to assemble first the augmented coefficient matrix and vector of constants. And then we'll be performing row operations to obtain the row echelon form of the matrix. The row echelon form, once the row echelon form is obtained, we can now solve the system by back substitution. So this is the augmented coefficient and vector matrix, or coefficient matrix and vector of constants. So the first target here is we'll make this number 4, 2, and 3 equal to 0 by row operation. So the row operation for row number 2 will be row 2 minus 4 times row 1, where the element in row 1 will be our pivot. And then for the row operation in row 3 will be row 3 minus 2 times row 1. And then for row 4 we have row 4 minus 3 times row 1. Okay. Again, the target is to convert these three elements into 0. Okay. So upon computation, we find the following new element values of row 2, for row 3, and for row 4. Next target naman natin is let's convert this number 8 and number 6 equal to 0. Same pa rin, we have to perform row operation. And let's use decimal instead of fraction, although using fraction is more accurate than using decimals. Okay. So for the row operation in the third row, we have row 3 minus 0.6154 of row 2. This value na 0.6154 is obtained from 8 over 13. Okay, para maging 0 itong number 8. And then for row 4, the operation will be row 4 minus 0.4615 of row 2. Itong 0.4615 is equal to 6 over 13. Okay. Then upon computation, we find the new elements of row 3 to be equal to that one. And for row 4, okay. So the next target naman is to convert this number 0.9225 into 0 by performing this operation. We have row 4 plus 0.3331 of row 3. And this 0.3331 is equal to 0.9225 over 2.769. Okay, so the new elements of row 4 will be this one. So we have now arrived at the row echelon form of the augmented matrix. So we can now solve the system by back substitution. When we say back substitution, we have to solve the system from the lowermost row going up, because the lowermost row is already an implication that one variable is already known, and once that variable is known, we have to use that value in order to solve for the other variable. Okay, and so on and so forth. So by back substitution, let's solve for z first. Okay, so itong equation na to is obtained from the lowermost row, which is equal to negative 0.6661 of z, which is equal to negative 1.999. Solving for z, we have z is equal to 3. So using z is equal to 3, we now solve for the next unknown variable, which is y. Okay, using the third row. Okay, the third row implies the equation negative 2.769 of y minus 2.231 times z, where z is equal to 3, and that's equal to negative 3.923. So solving for y, we have y is equal to negative 1. With known values of z and y, we can solve for x using equation number or the second row. Okay, so that's equal, the second row implies 13x minus 15y times 2z is equal to negative 5. So solving for x from that equation, we have x is equal to negative 2. And then lastly, we can now solve for the last remaining variable using the first row, which is w minus 2 times x plus 3 times y plus 0 times z, which is equal to 2. Solving for w, we have w is equal to 1. In summary, we arrive at the same answer as problem number 1, which is wxyz is equal to 1, negative 2, negative 1, and 3. And that's the final answer.